The date is December 17, 1944. Dawn breaks over the snow-covered forests of the Ardennes in Belgium. Through the morning mist, a column of German Panther tanks rolls forward, their sloped armor gleaming with frost, their long 75mm guns sweeping the tree line. These are the pride of the Wehrmacht. 45 tons of German engineering, nearly invincible from the front. Inside a camouflaged position, an American M4 Sherman crew spots movement. The loader reaches for a shell, but not just any shell. His hands wrap around something special, something that arrived just weeks ago in wooden crates marked Priority Air Shipment. The brass casing feels the same as always, but this round is different, heavier. The projectile itself gleams with an unusual metallic sheen. The gunner centers his sight on the approaching Panther, 800 yards, well within range for the German tank to obliterate them. But something has changed in this war, something the Panther crews haven't been told about yet. The Sherman fires. The tungsten core screams through the air at 3,400 feet per second, nearly twice the velocity of a standard round. It punches through the Panther's gun mantlet like a meteor through paper. Inside the German tank, hell erupts. The tungsten core fragments into dozens of hypersonic shrapnel pieces, ricocheting through the fighting compartment. Ammunition ignites, fuel vapor explodes. The Panther's turret lifts 3 feet into the air on a column of flame before crashing back down. The German crew never knew what hit them. This is the story of the M93 HVAP, the secret shell that turned the most feared tanks of World War II into burning coffins. A story of scientific breakthrough, industrial espionage, and a race against time to level the battlefield. Before we begin, hit that subscribe button and let us know in the comments if you've heard of HVAP ammunition before. Now, let's uncover the weapon that changed armored warfare forever. To understand why HVAP mattered, we must first understand the monster it was designed to kill. By mid-1944, the Panther tank represented Nazi Germany's answer to Soviet armor superiority. Officially designated Panzerkampfwagen V, the Panther combined the sloped armor principles of the Russian T-34 with German precision engineering. The result was terrifying. 80 millimeters of face-hardened steel mounted at 55 degrees on the glacis plate. When you account for the angle, enemy shells had to penetrate the equivalent of 140 millimeters of armor. The Panther's Rheinmetall 75mm KK-42 gun could knock out Allied tanks at ranges exceeding 1,100 meters, distances where American Shermans couldn't even dent German armor. Intelligence reports from the Normandy invasion in June 1944 revealed a shocking statistic. 38% of German tanks encountered were Panthers. This was far higher than anyone had anticipated. American tankers called encounters with Panthers death sentences. The standard 75mm gun equipped on most M4 Shermans literally bounced off the Panther's frontal armor at any range. Even the upgraded 76mm gun, introduced in July 1944, could only penetrate the Panther's gun mantlet at near-suicidal distances, about 91 meters or roughly 100 yards. At those ranges, the Panther's superior optics, gun depression, and firepower meant the German crow would usually get the first shot. And in tank combat, the first shot is often the only shot that matters. Field reports from France painted a grim picture. Lieutenant Colonel Alvin Gillum documented case after case of American tank platoons being decimated by single Panthers engaging from fortified positions. British intelligence confirmed the same pattern. The Panther excelled in open country, picking off Allied armor with near impunity. Something had to change. American tankers were dying in numbers that couldn't be sustained. The solution would come from an unlikely source: tungsten, one of the densest and hardest materials on Earth, and a crash program that would rewrite the rules of armored combat. Tungsten carbide wasn't new to warfare in 1944. The Germans had been experimenting with tungsten-cored ammunition called Panzergranate 40 since the early war years. The principle was simple but revolutionary. Replace the steel penetrator with an ultra-dense tungsten core traveling at extreme velocity. The physics were elegant. Armor penetration depends on kinetic energy concentrated into the smallest possible area. Tungsten carbide's density, nearly twice that of steel, meant you could fire a smaller, lighter projectile at much higher speeds. The higher velocity meant more kinetic energy. The smaller cross-section meant all that energy was focused on a pinpoint. But there was a problem. Tungsten was rare, desperately rare. Before the war, China had been the world's primary tungsten exporter. When Japan invaded China in 1937, those supplies were cut off. Germany initially received tungsten from Portugal and Spain, but Allied economic warfare and embargoes choked those supply lines by 1944. By mid-1943, German tungsten reserves were so depleted that Albert Speer, Hitler's Minister of Armaments, imposed strict limits on tungsten use in munitions. German Panzergranate 40 rounds became so scarce that tank crews were ordered to use them only in desperate situations. The United States and Britain faced the same shortage, but had better access to alternative sources. American tungsten came from mining operations in the western United States, South America, and whatever could still be imported from free China through treacherous supply routes over the Himalayas, the famous hump flights. Even so, tungsten remained a strategic material with competing demands. Machine tool manufacturing needed it. Light bulb filaments required it. Armor-piercing ammunition was just one application among many. The National Defense Research Committee and the U.S. Army Ordnance Department began serious development of high-velocity armor-piercing ammunition in 1942. The goal was clear: create a shell that could defeat German heavy armor without requiring a completely new tank gun. The existing 76mm gun would have to suffice. They just needed to make the ammunition lethal enough. The breakthrough came from understanding exactly how tungsten carbide behaves at extreme velocities and temperatures. Engineers at the Army's Ballistic Research Laboratory discovered that a tungsten carbide core, when properly designed, would remain intact during barrel travel and flight, then fragment in a very specific way upon impact. The core wasn't meant to pass through armor as a single piece. Instead, it was designed to shatter into dozens of hypersonic fragments after penetration, creating what one test report described as catastrophic internal effects. The M93 HVAP round for the 76mm gun weighed 18.91 pounds total, significantly lighter than the standard M62A1 armor-piercing round. But here's where the engineering genius appeared. The projectile consisted of a tungsten carbide core weighing approximately 4 pounds surrounded by an aluminum alloy body. The aluminum served multiple purposes. It provided a full-caliber sabot that engaged the gun's rifling, sealed the chamber for proper propellant combustion, and fell away after leaving the barrel, allowing the dense tungsten core to continue toward the target. Muzzle velocity was the key metric. Standard 76mm armor-piercing ammunition left the barrel at about 2,600 feet per second. The M93 HVAP screamed out at 3,400 feet per second, a 30% increase in velocity that translated to dramatically higher kinetic energy. Testing against captured German armor plates yielded stunning results. At ranges where standard ammunition bounced harmlessly off Panther frontal armor, HVAP could penetrate the gun mantlet out to 730–910 meters, nearly 10 times the effective range. Against the Panther's thinner side armor, HVAP was lethal out to 2,500 yards. But the real horror was what happened after penetration. Test reports noted that the tungsten core would fragment upon entering the tank's interior. These fragments, traveling at supersonic speeds and heated to extreme temperatures, would ricochet through the confined space, shredding equipment and crew alike. In tests against captured Panthers, the fragmentation effect was so severe that it often triggered ammunition fires even when the shell didn't directly hit the ammunition storage. HVAP ammunition began in early 1944, but scaling up proved nightmarishly difficult. The tungsten carbide cores had to be precision-machined to exact specifications. Even tiny imperfections could cause the projectile to tumble in flight or shatter prematurely against armor. Manufacturing tolerances were measured in thousandths of an inch. Each core required specialized machining equipment and skilled operators, both in critically short supply as American industry struggled to meet the demands of a two-ocean war. Initial production targets were ambitious, 43,000 rounds per month. Reality fell far short. By August 1944, when HVAP ammunition first reached combat units in France, only 2,000 rounds had been delivered, flown in via air transport because the situation was deemed that critical. Supply never caught up with demand. A typical M4 Sherman tank carried 71 rounds of 76mm ammunition in combat. By February 1945, 6 months after HVAP's introduction, the average Sherman crew had received exactly 5 HVP rounds. 5. The acquisition rate was approximately 1 HVAP shell per tank per month. This scarcity created agonizing tactical decisions. Tank commanders had to choose. Do you use your precious HVAP rounds on a distant Panther you might hit, or save them for a close-range emergency? Fire too early and you might waste your only advantage. Wait too long and the Panther's superior gun might kill you first. Combat reports reveal that many American tanks never received any HVAP ammunition at all. Distribution was haphazard, dependent on supply chains disrupted by the fluid front lines and competing priorities. Some tank destroyer battalions operating M10s with 3-inch guns, which could fire the same HVAP projectile as the 76mm, reported receiving adequate supplies. Others reported none. Meanwhile, German intelligence was picking up troubling reports from the front. American tanks that previously couldn't threaten Panthers were suddenly scoring penetrating hits at ranges thought to be safe. German tank crews began reporting catastrophic ammunition fires following impacts that shouldn't have penetrated. Something had changed, but they didn't know what. The first major test of HVAP ammunition came in September 1944 at the Battle of Arracourt in eastern France. General George Patton's Third Army, spearheaded by the 4th Armored Division, collided with German forces attempting to cut off the American advance. The Germans deployed over 250 tanks, including numerous Panthers from the 11th Panzer Division and the 113th Panzer Brigade. On paper, it should have been a slaughter favoring the Germans. Weather conditions were abysmal. Heavy rain and fog limited visibility and turned the terrain into a muddy nightmare. These were exactly the conditions where the Panther's superior optics and long-range gun should have dominated. But something unexpected happened. American M4 Shermans equipped with 76mm guns and precious HVAP ammunition began scoring kills at ranges that shocked German commanders. Panthers exploded from hits to their gun mantlets and turret sides. Tank crews that had felt invincible behind 100mm of armor suddenly found themselves vulnerable. One captured German tank officer, interrogated after the battle, expressed bewilderment. His Panther had been penetrated from the front at a range he estimated at 800 meters, impossible with the American guns he'd been briefed about. The impact had ignited the ammunition almost instantly. He was one of only 2 crew members who escaped before the tank became an inferno. The Battle of Arracourt ended with a stunning American victory. The 4th Armored Division claimed destruction of over 80 German tanks, including dozens of Panthers, while losing approximately 25 American tanks. It was one of the most lopsided armor victories of the European campaign. But Arracourt was just a preview. The real test was coming. By December 1944, German forces had assembled in the Ardennes forest for one final desperate offensive, the operation that would become infamous as the Battle of the Bulge. Hitler committed his last strategic reserves, including 400 Panthers. The plan was to split the Allied armies, capture the vital port of Antwerp, and force a negotiated peace in the West. What the Germans didn't fully understand was that American tanks were no longer the helpless targets they'd been in Normandy. December 16, 1944. The Ardennes offensive begins with a massive artillery barrage that turns the snow-covered forest into a hellscape. 3 German armies, over 200,000 men and 1,400 armored vehicles smashed into thinly held American positions. The surprise was total. Entire American units were surrounded and destroyed in the opening hours. The weather was so poor that Allied air superiority meant nothing. Aircraft were grounded by fog, snow, and freezing rain. Among the German spearheads, Panther tanks led the advance. The Panther had learned from its early mechanical problems. By late 1944, the Oskiv-Gay variant had improved reliability with strengthened final drives and better engine cooling. These were experienced crews, many veterans of the Eastern Front. They knew their business. In the town of crinkled Rocheroth, American forces prepared a desperate defense. The 644th Tank Destroyer Battalion, equipped with M10 tank destroyers mounting 3-inch guns, established positions among the buildings. They had HVAP ammunition. Not much, but enough. German Panthers charged down the main roads, confident in their armor superiority. What happened next was documented in battalion after-action reports that would be studied for decades. The Americans let the Panthers close to point-blank range, 200 to 400 yards, where HVAP was most effective. They specifically targeted the gun mantlets and the thin side armor. The tungsten-cored rounds punched through with devastating effect. One M10 crew reported engaging a Panther at 250 yards. Their first HVAP round struck the mantlet and penetrated. The Panther's turret lifted off its ring, propelled by the explosion of 79 75mm rounds cooking off simultaneously. The heat was so intense that the tank burned for 3 hours, its ammunition continuing to detonate in secondary explosions. Another tank destroyer knocked out 2 Panthers with consecutive HVAP shots, both striking the vulnerable junction between the turret and hull. The tungsten cores fragmented after penetration, shredding the fighting compartments. Neither Panther crew had time to evacuate. By the end of the engagement at crinkled Rocheroth, over 20 Panthers lay destroyed or abandoned. The American defenders had turned the town into what veterans called a Panther graveyard. The effectiveness of HVAP wasn't just about penetration. It was about what happened after the shell went through the armor. Captured German war diaries and post-battle reports reveal a pattern of catastrophic internal damage that Allied intelligence found both fascinating and horrifying. When asked to describe what happened inside Panthers hit by HVAP rounds, surviving German crewmen painted a consistent picture. The tungsten core, traveling at over 3,000 feet per second, would fragment upon entering the tank's interior. Unlike conventional armor-piercing shells that might pass through or remain intact, the tungsten shattered into dozens of hypervelocity fragments. These fragments, each carrying tremendous kinetic energy, would ricochet off the interior surfaces at unpredictable angles. Test reports from the U.S. Army Ballistic Research Laboratory described the effect as multiple projectiles within a confined space. The fragments would punch through equipment, sever control cables, and penetrate ammunition storage with equal ease. Because the Panther stored much of its ammunition in racks along the hull's side sponsons, these storage areas were particularly vulnerable. But the most lethal aspect was fire. Panthers, for all their fearsome reputation, had a fatal flaw that German tankers knew all too well. They caught fire easily. General Heinz Guderian, Inspector General of Armored Troops, had reported in June 1944 that the Panther is inclined to catch fire quickly. The fuel lines were made of porous material that leaked gasoline vapor into the crew compartment. The engine's cooling system often failed, causing overheating. Ammunition propellant was notoriously sensitive to shock. When HVAP tungsten fragments ricocheted through a Panther's interior, they created dozens of ignition sources simultaneously. The fragments were heated to extreme temperatures by air friction and impact. They would perforate fuel lines, puncture ammunition cases, and ignite the gasoline vapor that accumulated in poorly ventilated crew compartments. German crews reported that Panthers hit by HVAP rounds often experienced what they called instantaneous ammunition fires, the entire ammunition load detonating within seconds of penetration. Escape was nearly impossible. The time between impact and catastrophic explosion was measured in heartbeats. But HVAP's effectiveness came with a dark asterisk. German armor quality was declining catastrophically by late 1944. Allied intelligence teams examining destroyed Panthers in France made a disturbing discovery. The armor plates weren't performing as expected. In August 1944, U.S. Army officers testing Panthers at Isigny, France, found that 2 out of 3 examined tanks showed catastrophic cracking of the armor plate when struck by shells. The reason traced back to Germany's collapsing industrial supply chain. Armor plate steel requires specific alloying elements to achieve the right combination of hardness and toughness. Molybdenum was particularly critical. It prevented armor from becoming brittle while maintaining hardness. In 1943, Allied bombers had struck and severely damaged the Knaben molybdenum mine in Norway, cutting off a key German source. Supplies from Finland and Japan had also been interdicted. Without adequate molybdenum, German metallurgists were forced to use substitute alloying elements to maintain armor hardness. But these substitutes created a fundamental problem. The armor became brittle. Instead of deflecting or absorbing shell impacts, German armor plates developed a tendency to crack and spall, sending lethal fragments into the tank's interior even from non-penetrating hits. Post-war analysis of Panthers confirmed what Allied tankmen had suspected. Late-war German armor was significantly inferior to earlier production. The Brunel hardness ratings were maintained, but the impact resistance had decreased dramatically. Some armor plates would literally fracture when struck, with cracks propagating across the entire plate. This brittleness worked synergistically with HVAP's fragmentation effect. When a tungsten core struck degraded German armor, the plate would often crack extensively, allowing fragments to enter through multiple points. The armor that was supposed to protect the crew instead became another source of deadly projectiles. German tank commanders were aware of the problem but powerless to fix it. Some reports suggest Panthers were being prioritized for the remaining high-quality armor steel, while other vehicles like Jagdpanzer tank destroyers received inferior plates. But by late 1944, even priority allocation couldn't overcome the raw material shortages. The mighty Panther was becoming a death trap, and HVAP was exploiting every weakness. The Battle of the Bulge provided the ultimate test case for HVAP effectiveness under the worst possible conditions. From December 16, 1944 to January 25, 1945, American forces fought in brutal winter conditions against Germany's last major offensive. The weather was so cold that tank engines had to be started every 2 hours to prevent the oil from freezing solid. Visibility was often measured in yards, not miles. These were conditions that should have favored German armor doctrine. On December 15, 1944, one day before the offensive began, German forces on the Western Front possessed 471 Panthers, with 336 operational. This represented the highest concentration of Panthers ever assembled in the West. 400 of these tanks were committed to the Ardennes offensive. By January 15, 1945, only 97 operational Panthers remained from the units involved in the offensive. Total write-offs were listed as 198 tanks. This represented a loss rate of approximately 50%, catastrophic by any measure. How many of these Panthers fell to HVAP? The exact number is impossible to determine from surviving records, but after-action reports provide clues. The 644th Tank Destroyer Battalion alone claimed destruction of numerous Panthers using 3-inch HVAP rounds during the battles at Rocherath and Krinkelt. Similar reports came from Sherman tank battalions equipped with 76mm guns. What's particularly notable is the pattern of damage. German reports from the period mention with increasing frequency that American shells were achieving penetrations at ranges previously considered safe. Tank crews reported catastrophic ammunition fires following frontal hits, something that should have been nearly impossible with standard American ammunition. Some German units began modifying their tactics, specifically avoiding engagements at medium range where HVAP was most effective. Panthers that had previously advanced boldly in open terrain began operating more cautiously, keeping to reverse slope positions and longer ranges where HVAP's effectiveness decreased. But caution couldn't save them from the fundamental reality. The technological advantage that Panthers had enjoyed in Normandy had been dramatically reduced. American tanks were no longer helpless victims. The balance of armor warfare had shifted, and HVAP was a key part of that shift. In March 1945, a dramatic piece of film footage would become one of the most iconic images of the war's final months. A U.S. Army Signal Corps cameraman captured a remarkable scene in the streets of Cologne, Germany. An American M26 Pershing heavy tank, one of only 20 that reached Europe in time to see combat, stalked through the rubble-strewn streets, hunting a Panther that had already knocked out 2 M4 Shermans. The Pershing mounted a 90mm gun and carried HVAP ammunition. The duel was brief and decisive. The Pershing fired. The Panther exploded in a massive fireball, its ammunition detonating in a chain reaction that sent the turret spinning through the air. The footage became propaganda gold, but it also demonstrated what tungsten-cored ammunition could accomplish. Yet this dramatic footage obscures a troubling reality. HVAP remained in critically short supply right up to Germany's surrender. By March 1945, approximately 18,000 HVAP rounds had reached Europe for the 76mm and 3-inch guns. This sounds substantial until you realize the scale of operations. Thousands of American tanks and tank destroyers were in action. Distribution remained haphazard. Some units reported adequate supplies, others had none. The 76mm gun ammunition was split approximately 42% for tanks and 58% for 3-inch guns on M10 tank destroyers. But demand far exceeded supply. Tank crews learned to hoard HVAP rounds when they could get them, knowing resupply was uncertain. Intelligence reports from captured German documents reveal that Wehrmacht commanders never fully understood what had changed. They knew American tanks were suddenly more dangerous, but they attributed it to improved tactics, better crew training, or perhaps new tank models. The specific role of tungsten-cored ammunition remained mysterious to many German commanders until the war's end. Some reports suggest German intelligence did identify HVAP rounds from battlefield recovery, but by then it was too late to respond. Germany's own tungsten supplies were exhausted. Even if they'd wanted to produce countermeasures, thicker armor, spaced armor, improved metallurgy, the industrial capacity and raw materials simply didn't exist. The final revelation came from post-war technical intelligence teams examining destroyed German armor across Europe. The foreign material exploitation teams, specialists tasked with understanding enemy technology, conducted systematic studies of knocked-out Panthers. What they found confirmed battlefield reports but added disturbing details about exactly how HVAP killed. Internal examination of Panthers penetrated by HVAP showed a characteristic damage pattern. The tungsten core would punch through the armor, creating a roughly circular entry hole. But the interior damage was far more extensive than the entry wound suggested. Fragmentation marks scored every interior surface. Equipment was shredded. Ammunition had been detonated not by direct hits, but by secondary fragments. In several cases, investigators found evidence that crew members had been killed not by the initial penetration, but by the hypersonic tungsten fragments ricocheting through the compartment. The fragments were small, some weighed only ounces, but traveling at thousands of feet per second, they were as lethal as bullets. One particularly detailed report examined a Panther destroyed near Bastogne. HVAP had struck the gun mantlet, penetrated, and fragmented. The tungsten pieces had ricocheted downward, puncturing the ammunition ready rack near the gunner's position. The resulting fire had been so intense that the tank's aluminum components had partially melted. The crew compartment temperature was estimated to have exceeded 1,200 degrees Celsius, hot enough to cremate the crew in minutes. The psychological impact on German tankers was severe. Post-war interviews with captured panzer crews revealed deep fear of American guns equipped with the new ammunition. Many crews reported that late in the war they would immediately evacuate their tanks if they suspected they were facing American units known to have HVAP. This fear was rational. The survival rate for Panther crews whose tanks were penetrated by HVAP was estimated at less than 40%, far lower than for conventional armor-piercing shells. The combination of tungsten fragmentation and catastrophic ammunition fires left little time for escape. German tankers, who had entered the war confident in their technological superiority, now faced an enemy that could turn their most powerful tanks into burning coffins with a single well-placed shot. The climax of HVAP's story came in the war's final weeks, as Allied forces pushed into Germany itself. By April 1945, German resistance was collapsing, but isolated Panther units continued fighting with fanatical determination. The difference was that now virtually every American tank and tank destroyer had received at least some HVAP ammunition. The supply situation had finally improved as captured German rail networks allowed better logistics. Combat reports from this period show HVAP being used more liberally. Tank commanders no longer had to hoard their precious tungsten rounds. Engagements that would have been avoided in 1944, Panthers at medium range, hull-down positions, partially concealed targets, were now taken because crews had confidence in their ammunition. The effect was devastating for remaining German armor. Panthers that might have survived earlier engagements were knocked out with single shots. The psychological advantage had completely reversed. American crews actively hunted Panthers, knowing they had the means to kill them. One particularly revealing incident occurred near the Ruhr pocket in late March. An American tank company encountered 6 Panthers defending a road junction. In the ensuing firefight, all 6 Panthers were destroyed with HVAP ammunition. Total American losses: 1 Sherman damaged by a mine. The German crews, veterans of the Eastern Front with years of combat experience, never had a chance. But the real revelation came after the war, when intelligence teams gained access to German records and could conduct detailed interviews with captured tank designers and engineers. The Germans had known about Allied tungsten-cored ammunition since 1944, but had fundamentally misjudged its importance. They assumed it was being issued in small quantities due to tungsten scarcity, which was technically true, but they failed to grasp how effective even limited quantities could be when used at critical moments. German engineers had designed the Panther's armor scheme based on calculations assuming conventional steel-cored ammunition. The extreme velocity and fragmenting characteristics of tungsten carbide hadn't been fully accounted for. By the time they understood the threat, Germany's industrial capacity was too degraded to respond. The Panther had been defeated not just by superior numbers, but by superior chemistry and physics delivered in a 19-pound package. The aftermath of Hopp's introduction rippled far beyond the battlefields of 1944-1945. When Germany surrendered in May 1945, Allied technical intelligence teams fanned out across the devastated Reich, collecting captured Panthers for detailed examination. France alone recovered enough operational Panthers from Normandy to equip an entire regiment, 50 tanks that served in the French army until 1947. The French War Ministry conducted comprehensive evaluations of these captured Panthers. Their 1947 assessment was damning. Mechanical failures plagued the design. Armor quality had degraded severely in late war production, and the tanks showed a disturbing vulnerability to ammunition fires. But the report also noted something significant: extensive battle damage from what they identified as American sub-caliber penetrators. The Panther's reputation as an invincible supertank didn't survive contact with post-war analysis. Detailed statistical studies revealed that in actual combat, Panthers had achieved a kill-to-loss ratio only marginally better than the supposedly inferior Sherman. Much of the Panther's fearsome battlefield reputation stemmed from engagements in mid-1944 before HVAP became available. The tungsten versus armor race didn't end with World War II. The principles pioneered in HVAP development led directly to modern armor-piercing ammunition. Today's tank guns fire fin-stabilized, discarding sabot rounds with depleted uranium or tungsten penetrators, traveling at speeds that would have seemed impossible in 1944. The M93 HVAP was primitive by modern standards, but it established the template. Soviet designers studied captured HVAP ammunition intensively. Their post-war tank destroyers and tank guns increasingly relied on tungsten cord penetrators. The British, who had developed similar APDS, armor-piercing discarding sabot ammunition independently, continued refining the concept into the post-war era. But perhaps the most significant legacy was psychological. HVAP proved that technological advantage in armored warfare could shift rapidly. A tank that seemed invincible one month could become vulnerable the next. This lesson drove Cold War tank development, creating an endless cycle of improved armor versus improved ammunition, a race that continues today. The Panther crews who died in flames from Normandy to the Ruhr never knew they were victims of a revolution in metallurgy and ballistics. They just knew that suddenly, impossibly, American tanks could kill them. Today, the story of HVAP remains largely unknown outside military history circles. The drama of the Sherman versus Panther has been told countless times, but the critical role of tungsten cord ammunition is often overlooked. If you visit military museums housing World War II armor, you'll occasionally see HVAP rounds on display, unremarkable-looking shells with a subtle metallic gleam that hints at their tungsten cores. They don't look particularly impressive. No fins, no exotic shapes, just brass casings and metal projectiles. But these unassuming munitions changed the course of armored warfare. The numbers tell the story. In June 1944, American tanks were helpless against Panthers frontally. By January 1945, Panthers were being destroyed routinely at ranges previously considered safe. The difference wasn't new tanks. Most American armor in the Battle of the Bulge were still M4 Shermans. The difference was chemistry and physics delivered at 3,400 feet per second. Modern military historians debate whether HVAP was truly decisive or merely one factor among many in Allied victory. The answer is probably both. No single weapon wins wars. But HVAP gave American tankers something they desperately needed in late 1944, a fighting chance against Germany's best armor. The tungsten cores that turned Panthers into burning coffins came from mines in California, Colorado, and China. They were machined in factories by workers who never saw combat. They were delivered in wooden crates marked priority. And when they worked, when a Sherman gunner placed a shot perfectly and the tungsten found its mark, they transformed battles. The German Panther remains one of history's most iconic tanks, featured in documentaries and museums worldwide. But those beautifully preserved museum pieces rarely show the internal damage from tungsten fragmentation, the catastrophic armor cracking, or the ammunition fire scarring. They've been restored to showroom condition, their lethal flaws erased. Perhaps that's fitting. The Panther deserves its place in history as a formidable weapon, But so does the M93 HVAP, the secret shell that proved even the mightiest armor could burn. Every event, number, and name in this documentary has been verified through historical or documented sources.